All right, friends and neighbors, let's keep going with our math brain here and talk a little bit more about how we use some of the number systems or some of the calculations that we've talked about so far. So first up, when you look at a calculator and you have all of those math functions that you can plug in there, it turns out that a computer doesn't actually have all of those. We have to take a couple of really basic operations and sort of fit them together and find out how we can manipulate them to accomplish some of those same tasks. Now, an important thing to remember as we're going through this is that computers don't really talk numbers. Really, it's about electricity and getting circuits to do what we want. That is to say, get circuits to do some arithmetic for us or to behave as if they were actually doing arithmetic. So that's what the adder circuit was all about. Okay, so to begin with, we've got some basic functions that we have in a CPU. We've got add, negate, compare, and shift. And we'll talk a little bit about all of those and we'll do some examples. So adding is pretty straightforward when it's positive, right? When the numbers are positive, 5 plus 6 or 1 plus 2, or in binary, we're just adding 0, 1 to 1, 0, something of that sort. So very, very straightforward. But we have to remember that all of those numbers are sort of those counting numbers. We can't even say they're integers. So what happens when we want to deal with negative numbers or when we want to deal with floating point numbers? A whole different animal there, right? Something with a decimal or something that's fractional. A lot of that stuff we handle with something called the 2's complement notation. And in other cases, we need a completely different data structure. And we'll take a look at those later on. So the first one that we'll talk about is a compare, right? And really what we're after there is, are these two things the same? In other words, we might also be looking at whether or not one is bigger than the other one or smaller than the other one. So here's a basic circuit that we would find on the CMOS 4063. And credit to the folks that have this particular schematic. So we can see in the circuit that we've got a couple of things that we're used to seeing, AND gates. But what is that little dot at the end? Well, that is an inverter. So it takes whatever the gate gives you and turns it around. So while we can see the circuit here, we can also see on the right of the circuit the sort of logic that would give this. And so what we're looking at is, in the case of the upper AND, we've got two inputs, an A and a B, but the A is inverted, so the output of that AND gate is actually not A and B. And so this is a comparison between, a slight tweak to the inputs. And so what we have to think about is, when do we get an output from an AND gate? Well, we get that when we have two inputs that are both equal to 1. Well, in this case, we're inverting one of them, so it sort of changes the behavior. And then we have the output of the two AND gates, and they are fed into an OR gate with another inverter there. And so you can see the logic for that. It gets a little more complicated, right? And so what we're comparing here in the final analysis is we get outputs that indicate whether or not the value appears as being more than or less than the other one, or when they're equal. Now the whole thing can be sort of encapsulated in the XNOR, and the truth table is there. And on the truth table, we can see that we only get an output when A and B are both 0 or A and B are both 1. Now we use compare circuits a lot of times to decide when we're going to make a decision. So we might be making a decision when things are not equal. So we'll take some corrective action of some kind. Or we might understand that things are exactly what they're supposed to be, and so we're not going to do anything. So the compare circuits a lot of times are used to determine whether or not we're going to take action on something. Now a shift is pretty straightforward. It's exactly what it sounds like. We're going to take a value and move the values, move the binary digits one way or the other. What we get is a change in the binary because we've moved all the digits from one place to another. So you can sort of imagine that if we have a binary number like the one below, 0, 1, 0, 0, and we do a left shift, then we wind up with a 1, 0, 0, 0. And in that case, we're taking 2 to the second power, or 2 squared, and we get 4. But then we shift everything, and we get 2 to the third, which is 8. So shifting to the left doubles it. So that's what all binary numbers, right? If we just go and count in binary, we count 1, 2, 4, 8, 16, and so on. So when we shift the binary ones to the left, we wind up with a doubling. But if we imagine that that was exactly opposite, and we shifted from 1, 0, 0, 0, and we shifted right to 0, 1, 0, 0, we would be cutting the value in half. And so that's exactly what shifting does. Now, if we shift to the left, then we have to add a 0 on the right-hand side. And if we shift the other way, we would do the same thing. Now, shifting can occur in one digit, or we can do more than one at a time. So bitwise shifting is sometimes used when we want to do some kind of calculation that requires us to do something along the entire set of bits. So a very common example that we use in networking is when we're doing ANDing processes, when we have a number that we've converted to binary, and we're trying to say, well, what is the network that this IP address is on? We have to AND that IP address with its network mask, and that tells us the network. Well, we do that along the entire length of the 32-bit word, or the 32-bit IP address. And so that's exactly what we would have to do. We would have to go down all of the bits, do all of the calculations. Well, what would this value be? Well, as you can see, we started off with 1011, and that would be 8 plus 2 plus 1, which would give us 11. But when we do a 1-bit shift, all of a sudden we wind up with 16 plus 4 plus 2, or 22. So all of a sudden we wind up with, of course, a larger number. And each one of those bit positions has been doubled compared to what it was before. So the 8 became a 16, the 2 became a 4, and the 1 became a 2. Now, if we shift hexadecimal, and I think when we were talking about conversions, no matter what number system you're using, sometimes it's easier to convert to binary. And so a hexadecimal shift is easier to envision when you convert everything to binary. So we've got the hexadecimal values AA, and we shift both of those, and we wind up with a bit pattern there on the right, which will give us a 5-4. Now, a double shift would perform a very similar function, except, of course, we're shifting over 2 places, and so 7F in this example would be converted to FC. So let's talk about adding next. There are essentially 5 rules that we use for adding. And those are 0 plus 0 in binary gives me a 0. 0 plus 1 in binary gives me a 1. 1 plus 0 gives me a 1. 1 plus 1 actually gives me a 0. But we have to remember that we have a carry. Now, I suppose, to be more complete, we might say that 0 plus 0 equals 0 and 0 carry. 0 plus 1 equals 1 with 0 carry. 1 plus 0 equals 1 with a 0 carry. So now we understand why 1 plus 1 in binary is 2 in binary. And to write that value, it would be 1, 0. Well, that was because we had 1 plus 1 equals 0 plus a 1 carry. And then 1 plus 1 plus 1, which would be 3, right, will give us the binary values of 1, 1. But why do we have that? Well, we would have the sum would be 1, and then the carry would be 1 again. So these are the basic rules that we want to try and remember. Operationally, the last part there might be because we had a carry in, which is why I was adding 3 numbers instead of 2. We would have a carry in that we would have to deal with, and then a carry out. Well, how would n-bit addition work? To start, we have to remember that in the last place, we're dealing with a 0 and a 1, and so we would have a 1 in the sum, and then our carry would be a 0. So we just always want to remember that that's there, because we keep the 1, and the 0 is passed out. So there's no carry here in this case. So if we sort of step through this, right, we would get a 1 as the sum, carry a 0, and then we have a 1 plus a 1. Well, we know now that a 1 plus a 1 is a 0, and then we would have a 1 carry. And then we get into that situation where we have 1 plus 1 plus 1. So we have a 1 plus a carry of 1, or a sum of 1 and a carry of 1. That gives us a 1 in the last digit, and then we're going to fill it out. As a check, we can always say, well, what is the base 10 calculation that we would use? Well, the top number is 6 and the bottom number is 7, so we want is a 13 when we get done with this. And in the binary value that we have 8 plus 4 plus 1. So there we go. That's how it works out. Pretty straightforward, right? So far, so good. Now, sometimes it's a lot easier to see what's going on if we fill out the values of the remaining bits. So in the previous example, I was adding 4-bit numbers, and it's not always clear what's happening as we finish the carry. So in this example, let's fill it out a little bit. So let's assume that we're dealing with an 8-bit system, and we're going to represent our numbers in terms of 8 bits, not just with the number of bits that we need. So 13 from the previous example, instead of being 0, 1, 1, 0, 1, we would actually write it as 0, 0, 0, 0, 1, 1, 0, 1. So in that case, we're just filling it out with zeros on the left. And I'm also going to introduce the idea of being signed or unsigned. So when we are signed, we're actually going to allocate some of our bit space to the sign of the number that we're using. So all of a sudden we realize now that we could have 13 or negative 13. Well, how do you know that it's negative? We'll get to that in a second. But in either case, right, we can have overflow when we run out of room or we can't represent the number that we're trying to write down in binary. So we just have to be aware of that, and systems have a mechanism for handling that. Now, when we talk about signed versus unsigned, well, if it's unsigned, then everything's positive. And another way to think about that is that all of the binary values that we use, all of the bits, are used for the magnitude of the number that you're dealing with. But if we're signed, we have to have some way to represent that something's positive or negative. And it turns out that we take one of the bits to be 0 or 1 if it's positive or negative. And so all of a sudden we have fewer bits to represent magnitude. And so that's how we represent a negative number. If we're adding hexadecimal or octal numbers in the same way that we did the binary n-bit addition, by the way, n-bit just simply means that n is however many bits that you have. So if I say n-bit, I'm not describing a particular value. If I have 3 bits, then n is equal to 3 in that case. All right, so here I've got 4 hexadecimal numbers being added with 4 other hexadecimal values. And initially you might go, oh my God, how do I do that? But all you do is convert it to binary and then do the addition in the exact same way, and then convert back to hexadecimal. And there's the check for that. And if you want to, you can run through the bitwise addition from right to left. Now there can be easier ways, right? Sometimes you can just look at it and go, oh, I know exactly what that is. So b plus 1 is just c, which seems weird, right? But if you think in terms of hexadecimal, that's the way it works. In hexadecimal, 4 plus 3 equals 7, right? We don't really worry about it until we get beyond 9. And then the rest of the problem is right there. So sometimes it can be very easy, but if you're at all worried, just convert it to binary. All right, I think we're getting a little long here, so I'm going to stop this video. So head on over to part 2.